We've come to the end of our journey together. This is the last Chem 2070 lecture. And while we will be beginning a discussion of a new topic, gases, I hope you'll see that in discussing this new topic, it will be actually an application of the techniques you've learned earlier in this course. And I hope that you will be impressed how much acumen you've acquired in the understanding of the physical sciences. So gases. I guess gases in chemistry are the gases in the cylinders. Nitrogen, oxygen, hydrogen, and so forth that are in those cylinders and abound in the chemistry lab. But also gases, of course, are things of great beauty. It's hard to tell which is more beautiful. Is it the gases inside the balloons, or is it just the beautiful sky itself? But when a chemist looks at that beautiful gas, we see it differently. And hopefully you're beginning to see it differently. What we see are molecules moving about. We can think of them in this picture here. There are the molecules. They're just those little red blobs, which we know are actually Lewis structures and following VSEPR, but they're moving about. The arrows are showing how fast they're moving. And that's the way we chemists look at gases. What we see then are the physical variables. Gas molecules have an average velocity. And the average velocity that will work best for us is VRMS. RMS stands for root mean square. I'm not even going to give you the definition of root mean square. It's an average, and it turns out it's the easiest average for us to work with. And what else do we say looking at those gases? We see if you've got velocity, what are the two variables that you can think of? Put in chat, what are the variables that come out of velocity? What's the most important variable that comes out of velocity? Yes, the most important variable is the kinetic energy, which I'm going to call translational. And what I mean by the translational kinetic energy, this is going to be a really stupid picture of a car. And what I want to get here is the car. It's moving, but translational kinetic energy is the motion that it's moving. These wheels are rotating. Rotation is not part of E-trans. And we'll be calling E-translational E-trans. And the relationship between E-trans and the velocity is E-trans equals 1/2 m VRMS squared. And the mass, here, let me move this over. The mass for a gas is the number of moles times the molecular mass. So that's the molecular mass. And therefore we get the important formula E-trans equals 1/2 m, so it's 1/2 m VRMS squared, and that's equal to 1/2 n mm VRMS squared. And one of the most interesting things is that we can actually tell. We actually have a way as human beings of telling E-trans in things. And all you have to do is hold out your hand and feel the temperature of the room. Here, I'm holding on my hand right now. As you see it, I'm feeling the temperature of the room. And it turns out that E trans is actually, your hand is a sensor, is actually proportional to the temperature. And by temperature, I mean the absolute temperature. The exact relationship between the temperature we feel in our hands and the air is E trans equals 3/2 N R T, where R, I have to put that over here, excuse me, where R equals the gas constant, and T is absolute temperature. So the two relationships we have are E trans equals 1/2 N mm VRMS squared, and E trans is equal to 3/2 NRT.